Binary trees are a great data type to use to store some information. These trees are built with nodes. The nodes contain some data in it, then two links to its children or subtrees, one to the left and one to the right. The children are the same node type, so it's a repeating or recursive data structure. The nodes can have one, two, or no children depending upon what we put in it. So it's completely possible to have a node with a singular giant subtree. But man, does it really hurt to see it. We call the top node of the binary tree the root node. The nodes with no children, the ones at the very bottom, are called the leaf nodes. Think of it as an upside down tree, because computer scientists apparently have never seen an actual tree. A level is a set of nodes with an equal distance to the root. If we choose what information each child can hold, we can turn these binary trees into binary search trees. BSTs for short are a great data type you can use to sort data in an easily searchable manner. The condition we'll put is that we will put values less than or equal to our node on the left, and values strictly greater than our node on the right. With this rule, if we are looking for a node, we just need to know whether we are on it or its relative position to our current node. Let's run through an example with this list: 56, 17, 24, 78, 67, 98, 5, 2, 15, 31, 71. So we will first insert 56. Okay, that will go at our root. Oops. Next, we will insert 17. We'll compare that to our root. Okay, 17 will be less than our root, so we go down the left child of our root. Since there's nothing here, we can insert 17 here. Next, we'll insert 24. Comparing 24 with 56, 24 is less than 56, so we'll go down to 17. Comparing 24 with 17, 24 is greater than 17, so we'll go down to the right of 17, and we'll have 24. Next up is 78. 78 is greater than 56, so we'll go down the right. We see there's nothing here, so we're going to put 78 here. 67. 67 is greater than 56, so we'll look at the 78 and less than 78. So we'll go to the left of 78 and draw our 67. Oops. Next, 98. 98 is greater than 56 and greater than 78, so we'll go down to the right twice to get to this position and plug in our 98. 5. 5 is less than 56 and less than 17, and 17 has nothing to the left of it, so we'll just draw a 5 here. 2 is less than 56, less than 17, and less than 5, so we'll just draw the 2 right here. That takes care of these three numbers. 15. 15 is to the left of 56, to the left of 17, but greater than 5, so to the right of 5. 31. 31 is less than 56, greater than 17, and greater than 24. And lastly, 71. 71 is greater than 56, less than 78, but greater than 67. So here is our binary search tree. Let's say we would like to delete the node 17. What happens when we delete? When we delete, we will get the successor. This is also known as the leftmost node of the right subtree, which is also known as the least of the greatest elements of the children, which is also known as the correct answer in this scenario. So if we remove 17, we're going to be looking for the successor. So in this case, the leftmost node of the right subtree is 24. We'll move up this 24, and we'll have to replace whatever is here. In this case, it will be a 31. And that's how we would delete a node 17 from this tree. That concludes this week's tutorial on BSTs. Sorry the video came out a bit late. We were busy with the midterm. See you next week. Hey y'all, Will here. Have you ever had too many books on your bookshelf? Like by the time I'm done looking for the book, I've already read a novel's worth of titles. If only there was a good way to search for something. Oh, here's one.